Okay, let's unpack this. If you're someone who tracks digital content creation, especially in the 3D space, you already know the big bottleneck. It's just computationally crushing to generate a truly high-resolution object that has both complex geometry and realistic, surface materials. Today, we are diving deep into a new method that seems to fundamentally break that bottleneck.
Well, the mission of this research was really to solve a massive trade-off. Historically, with 3D generation, you had to choose. You could either create basic shapes pretty efficiently, or you could create these extremely complex shapes with arbitrary topology.
And when you say arbitrary topology, you mean things like open surfaces or structures that loop back on themselves, or even intricate hollow interiors.
Right, and you could do that, but it came at a huge computational cost, and often without any realistic materials attached.
So the sources we've been looking at, they introduce a solution that's built on two pillars. There's a new representation they call the O-Voxel, and it's combined with a highly specialized compression architecture. And here's the core takeaway, the part that should really grab you. This new approach gets substantially higher geometric and material fidelity than its predecessors, but it does it while using dramatically fewer latent tokens to encode the object.
And that compactness is really the engine of its efficiency. When we talk about performance, we're talking about generating fully textured, massive assets. I mean, things as high resolution as 100, 500 to 363.3. And doing that in about 1 minute.
That speed, combined with the quality of the details, makes this approach a potential, game changer for production pipelines.
Yeah.
So let's start with that foundation, the O-Voxel. It stands for omni-voxel representation. Why did the existing infrastructure fail? What made this new structure necessary?
It really comes down to the limitations of the existing 3D representations. Most of the large 3D models today, they rely on what are called isosurface fields, things like signed distance functions or SDFs.
Right.
And you can think of an SDF as defining the world by calculating the shortest distance from any point in space to the surface of an object. It works great for solid, simple shapes.
It's sort of like modeling a smooth, watertight balloon.
That's a great analogy, but that inherent design, it mandates constraints. SDFs struggle profoundly with arbitrary topology. They require these manifold, watertight structures.
So if you try to model a sheet of paper, or maybe the Venn fence,
It gets confused. And critically, these field-based methods, they also tend to neglect comprehensive appearance data. You know how light interacts with the material, which is fundamentally correlated with the shape itself.
So O-Voxel steps in as the field-free solution. It's a sparse voxel structure that acts as a robust nexus, encoding both geometry and appearance natively. So how does it manage to capture that complex geometry if it's not relying on fields like SDFs?
The key innovation is in its flexible dual-grid formulation. It's inspired by, but it's distinct from, traditional dual contouring. Now, dual contouring is a known technique for extracting surfaces from voxel data. But instead of relying on a pre-existing scalar field to tell it where the surface is, O-Voxel just bypasses the field entirely.
Okay, so if it's not reading a field, what is it reading?
It goes right to the source, the input asset's mesh surface. It uses that mesh to determine intersection flags for the edges of the voxels, and it assigns what they call Hermite data.
Hermite data.
Which essentially gives us two pieces of information at the intersection points. The exact location of the intersection and the surface normal, which is the direction the surface is facing.
That seems much more direct than, trying to fit a field around the whole object.
Yeah.
But how does it determine the final position of the resulting vertex in that dual grid? The new corner of the mesh it's extracting.
That's where the power of the QEF comes in, the quadratic error function. A standard QEF calculates the best compromise spot for a new vertex that minimizes the error to all the incoming Hermite data.
It's like a group of surveyors all pointing to different spots on a wall, and the QEF finds the one best location that makes everyone the least wrong.
That's a good way of thinking about it.
And the sources point out that they didn't just use a standard QEF, they made two critical modifications. This must be where the geometric fidelity for complex objects comes from, right?
That is the insight. To improve the modeling of difficult open shapes like that sheet of paper or a complex boundary, they introduced two additional error terms into the QEF calculation. The first one is specifically for boundary edges. This term guides the dual vertex to align accurately with those open boundary edges, and that dramatically improves how open surfaces are represented and extracted.
So it's explicitly aware of where the object ends instead of just pretending everything is closed.
That's it. The second term is a regularization term, which basically ensures a smoother, more even distribution of the resulting vertices. This helps prevent jagged or noisy artifacts in the final reconstructed mesh. So the geometric feature, what the model actually learns, it comprises that calculated dual vertex position, the edge intersection flags, and what they call splitting weights, which guide how the squares of the dual grid are adaptively subdivided into triangles.
Okay, so we've covered the geometry, including the tricky parts like open surfaces. Now, appearance. You mentioned O-Voxel encodes geometry and appearance together. This must be essential for getting high-quality assets.
It is, because geometry and material properties are just intrinsically linked. The O-Voxel models arbitrary surface attributes that are aligned perfectly with the geometry, specifically implementing physically based rendering, or PBR, parameters.
And for our listeners, PBR just means the digital object behaves the way light does in the real world, how it reflects, how shiny it is, and so on.
Correct. The material feature, what they call 5-mat, it contains 6 channels. You have the base color, the metallic ratio, which says if it's a metal, roughness, which determines how scattered reflections are, and, crucially, opacity, or alpha.
The alpha channel.
That inclusion of the alpha channel is what allows the model to inherently handle translucent surfaces, like realistic glass. That's something that often causes previous generation methods to just completely fail or produce really unnatural results.
And because it's a volumetric representation of these attributes, it allows relighting after the fact, which is huge for production.
It is. You have the full suite of material data stored. But let's step back and just look at the efficiency of the O-Voxel itself. The source emphasizes its instant bidirectional nature, which is a key advantage.
That conversion speed has to be fast if you want to scale this up.
It takes only a few seconds on a single CPU to transform a complex mesh into the O-Voxel structure. And it's so fast because the process is optimization-free and rendering-free. It's just direct calculation. Even better, reconstructing the mesh from the compressed O-Voxel takes only tens of milliseconds.
So you can iterate and train much, much faster than with methods that rely on, time-consuming field optimization or rendering steps.
Yeah.
Okay, so we now have this dense, comprehensive, high-fidelity building block, the O-Voxel. But to handle these massive resolutions like 100, 330, and 63 drives, we have to compress that data down efficiently. And that's the job of the Sparse Compression VAE, or SCVAE.
The goal of the SCVAE is paramount. Create a compact latent space that's memory efficient and easy for the generative model to learn from, all while retaining almost perfect fidelity. And the SCVAE achieves a high 16 times spatial downsampling ratio.
The 16 times spatial reduction is enormous. That sounds like trying to squeeze a massive complex blueprint onto a small sticky note.
It is a phenomenal compression rate. The paper states that a fully textured 100 and 243.3 resolution asset, which is just incredibly detailed, can be encoded into approximately 9.6 thousand latent tokens. And the amazing part is that this compression results in what the researchers describe as negligible perceptual degradation when you reconstruct it. The details are still there.
Achieving that high compression without the model just forgetting important geometric details.
Yeah.
That must have required some specific architectural tricks inside the VAE. It can't just be a standard autoencoder.
It couldn't be. Since the data is sparse, most of the volume is empty space, and the data is only on the surface, the VAE uses a fully sparse convolutional U-shaped network that's efficient at high resolutions. But they introduced 2 major innovations to manage the high compression.
Let's talk about the first one, which deals with how the data flows during compression.
The first innovation is the sparse residual autoencoding layer. In a standard VAE encoder, as you compress data, important information can just get squeezed out. This new layer uses non-parametric residual shortcuts, you can think of them as side channels, to rearrange and preserve crucial information between the space and channel dimensions in the sparse grid.
So it stops the model from just forgetting those sparse details when it has to squeeze the data down so tightly.
That's the idea. It's a way of mitigating that challenge, ensuring the rare, important details don't get lost in the noise. And the second innovation addresses the computational efficiency of the VAE's core processing block.
The optimized residual block.
Right. Standard sparse convolutions can become pretty inefficient when you're dealing with data this sparse, especially when you stack them. So to enhance the model's ability to learn nonlinearity, its ability to recognize complex patterns, without adding massive overhead, they substituted the standard convolutional layers. They used a single sparse convolutional layer, followed by a wide, pointwise multilayer perceptron, an MLP. This MLP acts a bit like the feed-forward network you find in transformer models. And this substitution significantly enhances the model's ability to learn complex relationships and improves the reconstruction quality without sacrificing efficiency.
The paper also mentioned a critical two-stage training approach to stabilize the whole learning process.
Yes, because of the complexity here, the learning had to be managed carefully. The first stage focuses on stabilizing learning quickly at a lower resolution. It does that using direct feature regression on the O-Voxel features. Once that's stable, the second stage increases the resolution and introduces rendering-based perceptual supervision.
So they're basically telling the model, hey, look at the high-resolution output, make sure it actually looks right to a viewer.
That's right. They render intermediate outputs like mask, depth, and normal maps, and then supervise them with a blend of different losses. This multimodal supervision is what really enhances the fidelity for that high-resolution output. A final point on structure is that they learn two decoupled latent spaces, one for shape, one for material, and that facilitates the sequential generation scheme later on.
So this compact, structured latent space is the key. It feeds into the final generative framework, which uses these massive flow-matching models. What does that final system look like, and how does it actually execute the generation?
The system uses diffusion transformer, or DIT-based architectures. They total about 4 billion parameters. And since the latent space is decoupled, the generation unfolds in 3 sequential stages. First, the model generates the sparse structure. Second, it generates the geometry using that shape latent space. And third, it generates the material, which models the PBR properties right in 3D space, conditioned on both the input image and the geometry it just made.
And the efficiency numbers, which are enabled by that extreme compression, are just astounding.
The pipeline is incredibly efficient compared to other models. They report generating fully textured assets in approximately 3 seconds for 500 and 223 resolution, 17 seconds for 100 and 200 and 403 $3, and only 60 seconds for the truly massive 100 and 363 3-way resolution. And that's on an NVIDIA H100 GPU.
That speed makes complex, high-res 3D creation feel almost instantaneous. But beyond speed, how does the quality hold up? Let's talk reconstruction first, how well it copies an existing asset, and then full, novel generation.
For reconstruction quality, the results consistently show superior performance. The method outperforms 4 representative baselines across key metrics like mesh distance and normal PSNR. And crucially, it achieves this superior geometric fidelity while encoding the object with a substantially smaller number of latent tokens. It just confirms that finer details preserved even under heavy compression.
And when it's generating entirely new assets from scratch.
Qualitatively, the results are striking. The assets have intricate geometric details, sharp surface features, and they successfully handle those challenging assets that usually confuse older models.
You mean the thin structures, the complex enclosed interiors?
And difficult translucent or reflective materials like realistic glass and metal. Quantitatively, the method achieved the highest alignment score across all the tested multimodal models, including ULIP2 and Uni3D. And in user studies, the perception of quality was overwhelming. The method was highly favored by participants, achieving a 66.5% preference rate for overall quality.
It's also worth noting the flexibility built into that material generation stage.
Yeah. It is. Because the material generation stage is decoupled, it can be used independently for 3D PBR texture synthesis. And this is a major technical advantage. Because it operates natively in 3D space, it completely avoids the inconsistencies and seam artifacts that are chronic challenges in, say, multi-view or UV-based texture approaches, where you're trying to stitch flat images onto a complex 3D shape.
So, to synthesize the entire advancement here, the O-Voxel representation gives you the comprehensive, field-free, high-fidelity building block for geometry and PBR materials. Then the SCVAE delivers the structured, highly compact latent space you need for scaling. And together they allow these massive flow-matching models to generate superior, high-resolution 3D assets with unprecedented efficiency.
That summarizes the fundamental architectural change, but it is essential to look at the inherent limitation discussed in the source, particularly when it comes to spatial resolution.
That's a critical thinking point. Since O-Voxel is still based on voxels, where does its representation power hit a wall?
Like all voxel methods, its fidelity is bounded by its spatial resolution. If geometric features are extremely small, let's say you have 2 very thin parallel surfaces that are closer together than the voxel size, the QEF solver that's trying to find the new vertex position will just place it right in the middle.
It's minimizing the error to both surfaces at once.
Right, which results in a blurred or averaged position. Similarly, the volumetric material attributes in that voxel become an average, and that leads to a blurred appearance or aliasing when the features are too small.
So it's a limitation shared by the category, but the system still pushes the frontier because of the sheer scale and efficiency it manages to achieve.
It does. That compression power and efficiency allow for flexible scaling at test time. You can choose to increase the computation within the training resolution to improve quality, or you can actually scale up the resolution efficiently, synthesizing shapes beyond what it was trained on, like reaching 153 to 363 $300.
So what does this all mean for the future of digital content? I mean, consider the power of encoding a massive, physically accurate, high-resolution object like a fully detailed piece of heavy machinery or a complex architectural facade into such a small, manageable number of tokens, less
Yeah.
than 10,000 instructions. That level of data compression and fidelity fundamentally shifts the economics and scalability of content creation, making highly detailed 3D assets a commodity generated almost instantly.